Okay, so let's get started. Okay, so let's get started. I'm just sharing the screen. Yes. Okay, so just to recap what we have seen, let me check if I'm recording or not. Then yes, okay, and yeah, just to recap what we are trying to see here is we are trying to understand the anatomy of a transaction. So basically, we are trying to understand how the transaction works, how the transaction can be validated, and we have seen that it contains two parts: the signature part and the script public key, which we also call it as some kind of locking and unlocking script, right? So let's try to understand that, right? So basically, again, we are taking a very simple example of somebody's a very simple transaction example: pay to public key hash. What does it mean? So somebody transferred to a public key, and the owner of the public key, using his private key, is trying to spend the coins, right? So, and then briefly introduced the notion of the locking script and unlocking script. I briefly talked about those concepts, but let us try to understand what they mean and things like that, right? So again, take this example. Alice got 17 coins. Bob got 17 coins from Alice, and then he's trying to spend these coins, right? So, and I was talking about two parts. One is the script public key, which is generated when Alice transferred 17 coins to Bob. So this is the part where it generated. And there is another part, which is unlocking script, which we call it as script signature, which is generated when Bob is trying to spend these coins, right? So the script contains, whenever you want to validate a transaction, it contains two parts: the locking script and unlocking script. So let us try to understand what is locking script and what is unlocking script, right? So, so the locking script, now I'm talking about the locking script. So locking script generated when somebody transfers coins to you. And a locking script is a spending condition that is placed on an output. So it specifies the conditions that must be satisfied to spend this output in future, right? So this is what locking script. It's a bit complicated formally, but let me take a simple informal example. Maybe it's a stupid example, but at least it tries to give you the background, the intuition behind this locking script, right? Let us say that you are studying at SRM University, right? And let's say that your family want to send some money for your expenses, for your living expenses in Chennai and things like that, right? So let's imagine that your family has a pool of money. It could be in cash or it could be in the bank or whatever. Maybe we ignore all these projects. Let's say that your parents send some money to your bank account so that you could use them for your living expenses, right? So that is a kind of log script. Let's say since they have a pool of money and now they are transferring this a small amount of money from this pool of money and transferring to your account is some kind of locking script, because this money, transferred money, you only can spend it. None other than people can, even from your family members, they cannot spend it because the money is transferred to your account, right? So this is a kind of locking script where they are trying to put a condition on the small part of the money, saying that you only can spend it, right? The way they specify the conditions on this money is by transferring to your bank account, right? So let us call that as the locking script, because the locking script enforces some conditions on a resource. In this case, the money for your living expenses, which is, and the way we put this we put the conditions is that, okay, we transfer the money to student X so that student X can only spend this money. So that is the condition which we are enforcing here, right? And in order to spend this money, the small part of the money which is transferred to your account, we have to satisfy the conditions, then only you can spend money. Let's see how that will also happen, right? So locking script is a script public key. It contains the public key. And again, now I'm back to the Bitcoin, right? So a locking script contains the script public key. It contains instructions about the how to validate the public key and things like that. It contains public key and or the Bitcoin address and things like that. And in most of the applications, a last script appears as a source code, as a script public key, and it could be much more complicated as well. For the time being, just postpone it, and then we say that locking script contains instructions about the public key and the conditions which needs to be satisfied by the which needs to be satisfied to spend the resource on which this public key, this condition is imposed, right? Okay, now let us go to the unlocking script. Again, now we are in this part. So now we are talking about unlocking script. And now, so we are trying to spend the resource, right? So an unlocking script is nothing but it solves or satisfies the conditions based on placed by the locking script and allows output to be spent and as part of every transaction's input. Again, let's get back to our stupid example. Let's say that your family has sent this money to your bank account. So where they enforced a condition saying that only you can spend this money. None other than else can spend this money because the money is transferred to your account. So which is like some kind of locking script which they put. Only not even they can spend this money because it's already in your account. So that is the locking script part. Now let us think about how unlocking script works in this example. Let's say that you have a bank account and you have a card, right? A bank card connected to your account. So what you do is whenever you want to spend this money, you will use the card, which is satisfies the condition of saying that, okay, you are spending this money, right? Let's say that the money is sent to a student called Siddharth, and Siddharth will present his card. He will use the card connected to his bank account, so which satisfies the condition saying that, okay, he only is spending this money, right? He only is consuming this money. Ignore all other things like what happens if the card is stolen, those kinds of things, ignore it. But again, coming back to the Bitcoin, unlocking script is nothing but it satisfies or solves the conditions which are put by the locking script, right? If you take a simple way, what I mean to say is, let's say that if somebody transfers coins to me, when I want to spend these coins, I'm just satisfying this condition saying that the coins are transferred to my public key. I'm using my private key and generating signature to satisfy so that it satisfies the condition, because the public key and private key and the signature validation, all these things happen. So since the conditions are satisfied, I can use this resource, right? So the unlocking script was called the script signature. Basically, it contains it contains a digital signature, and unlocking script acknowledges the much broader range of the locking script requirements. So for example, you could have multi-signature and things like that. And then let's say that if you have multi-signature in the locking script, specified in the locking script, and the unlocking script will satisfy that conditions. For example, if you have 3 out of 5, and the unlocking script will also say that which 3 the signatures are included in it, and things like that. So many things will happen a bit later. So any questions so far? Are we good with locking and unlocking script and other kinds of things? Because now we are going into much further. We are looking into how to validate a transaction and things like that using the scripting language and stuff like that. So if you have any questions, ask now. Otherwise, it will be a bit more complicated. It looks like you don't have any questions, or should I wait for a few more seconds? You can also put it in the chat if you have any questions, right? Okay. So it looks like you are with me. Yeah. So good. So let's briefly talk about the Bitcoin scripting language. So basically, it's a small scripting language built for the Bitcoin only. And it is a language inspired from a language called Forth. It's a very, again, a small language, but it's called Forth. And it is simple and compact. It has support for cryptographic functions, for example, signature validation and hashing and all other other functions are implemented in this one. And most importantly, it's a stack-based language. Do you have a course on compilers in your degree program?
Sir, it's in next semester, sir. Compiler designs.
Okay, so it's okay. Next semester. Okay, so then you will come across the stack-based language. So basically, compilers normally work on the stack-based language. So they copy data to the stack and things like that. So I have some examples to show you. So it's a stack. Even the Bitcoin scripting language is a stack-based language. I will show you how the stack-based language works and things like that. And then it limits on the time and memory consumption. So it's as I mentioned before, it's a very, very small scripting language. So it has no looping. So that means you cannot write for and while loops, infinite loops and things like that. So it only have very, very few constructs. And it is not Turing complete. You know, Alan Turing, he is who we consider as the father of the computer science, and so he has the notion of Turing completeness. So he's the one who didn't build a computer, but he's the one who come up with a logical model for how computing work and things like that. So whenever you have programming languages or new programming languages or any scripting languages, people will test it against this Turing completeness. What does it mean? A Turing completeness is given infinite amount of resources and other kinds of things, whether a language could encode a function or not. So I'm putting it to very simple steps, but what people will do is people will test the programming language against the Turing completeness. And most of the programming languages, for example, Python and other kinds of languages, they are Turing complete. So they can encode any kind of complex functionality. But Bitcoin scripting is not a Turing complete because it doesn't allow loops and other kinds of things. Right? So yeah, you can look into here what is Turing completeness and things like that. And it's a simple stack-based language, means that every instruction is executed only once linearly, right? And it will be executed in sequence. And no looping construct, so we know how many exactly steps this execution will complete. So it's equal to the number of instructions and things like that, number of steps in the script and things like that. No infinite loops, not Turing complete, means it's not possible to encode powerful functions. So that is the main Turing completeness. And again, what is the result of this script validation? When you execute a script, it will only give pass or fail, or you can say success or fail. If you get success, then the script is valid, which indicates that the transaction is valid. So the transaction will be included into the block, right? On the other hand, if you get a failure, if the script execution returns a fail, then it will not be included to the transaction. It will not be included to the block. So that is the main criteria all the miners will use. And we will see why miners will only use this strategy in the next class when we talk about mining. I don't think we have talked about mining, right? It is coming in the later classes and things like that. Okay. So some more information about scripting language. Script was designed with a limited scope and executable on a range of hardware. So the reason why they went for a very scripting language, you can see when you compare with the Ethereum, they have they have a scripting language as well. Their scripting language is much more powerful because it can encode a lot of complex logic and things like that. In case of Bitcoin, the main purpose of using a very simple language is that you can execute them on various range of hardware and even on a simple embedded device and things like that. So that is the reason why they went for a very simple design. And it requires minimum processing. You don't need a fancy what you call CPU to execute them and things like that. So very minimal requirements. This is a deliberate security feature for to use in validating in the programmable money, right? So since you need to do validation at many different scenarios, so that's why they went with a very simple design. Of course, remember, nobody has imagined even when Bitcoin was designed, right, by Nakamoto and his group, whoever it may be, right? And their intention was very simple design. They went very simple design. They used a hash, 32-bit hash and things like that. No, they used a 32-bit hash and things like that. The main idea is to such that you can do mining on your simple laptop or a simple computer. So that is the main design criteria behind the design of all these things. So that's why the scripting language is also very simple, so that you can easily use normal computing devices to verify it. Okay, so now what I will do is to introduce how stack-based languages works and how a script can be validated and things like that. Let me take a very simple example. Again, I'm using an example which is encoded in the Bitcoin scripting language. So here what I'm trying to do is I'm just trying to verify whether 2 + 3 is 5, right? So this is a very simple arithmetic calculation, but I just want to introduce how stack-based languages works and how they will be executed and things like that. Of course, we don't need a Bitcoin scripting language and expensive validation for just checking whether 2 + 3 is 5 or not. But the purpose of this is to understand how the hash-based, stack-based scripting languages works and things like that. So let's say that we want to verify 2 + 3 is 5 or not. So this is how it is encoded into the Bitcoin scripting language. You have 2, 3, op add, 5, op equal. Let's go step by step, right? Again, this is a sequence stack-based language. So one item at a time will be processed. And then you have two types of things in the scripting language. Either you have values, for example, 2, 3, these are the values, 5 is also a value. Or you have these funny op_add, op_equal. These are the operations, you can say, right? These are the operations which will do some action, right? So, for example, op_add means it will add the preceding two numbers, and op_equal means it will check whether the preceding result and this result is equal or not. Okay, this is the example. Let's go step by step. So here you can see I have the stack. This is the stack, right? So this is the stack. So stack is like, how can I say? Let's say that you go to a dinner and you have a pile of plates, right? So what you do is you take the from the top, right? So you take all the from the top. First in, first out. No, last in, first out, or something like that. So that is you will only take it from the top, right? So, and whenever you meet a value, so the idea is that simply that value will be copied to the stack, right? So now we start with here. So now we are here. Let's say that the interpreter encounters this first value. So the basic operation is just copy that value to the stack. So now we have the value copied to the stack, right? So this step is executed. Now let us say that it goes to the next step. And again, we have a value. So we just simply copy the value on the top. Remember, this is the stack. So you put from the top and you take from the top, right? So this is not a queue. queues work in a different manner. Queues you will add to the queue. So, and the first in, first out. The concept of queues is the one who get into the queue first, they will go out, right? So similar, unlike queues, the stacks is like last in, first out, something like that. So now we copy 3. So there is nothing much happened. Now let us go to this one. So now we have this step, add. Let me execute that. So that means it's an operation called the op add. So it will do some function. What it does is, whenever you see this add function, it takes 2 preceding values. Where are the values? The values are always in the stack below the current instruction. So this is the current instruction. So it will take the 2 values preceding in the stack, and then it will simply compute the addition, right? So let me execute this step. Now you can see here. So basically it will, I think just 1 second, this animation is not working properly. Maybe run it again. So you have 2, you have 3, and then you have up, then you will get a 5. So you can see here, then you will have 5. Yeah, the animation is, I try to do it, but it's giving some problems, right? So you can follow here. So we have 2, 3 added to stack, and we perform this operation, and the result of 2 plus 3 is 5. So basically, we copy 5 in place of these 2 things. Now it will work. Yeah. So we will place, because the result of 2 plus 3 and op add is 5. We clean all those things, and then we put replace with 5. Right. So now we have 5. Right. So now we are in this step. The result of executing this add step is it will put 5 on the stack. Okay, let's go further. And now we are at this point. So we come to here. This is a value. So we just copy the value to the stack. So we also put 5. And then we go to the next step. We are here now, equal. And then what it will do is it will copy the equal operation on the top. And then the result of the equal operation is that it will check the preceding 2 values. So the preceding 2 values are 5 and 5, since they are equal. So it will simply return true. Right. So I will run the animation one more time so that we can understand what's happening and things like that. So what we want to do is we want to execute this step 2, 3, op add, 5, op equal. So basically trying to verify whether 2 plus 3 is 5 or not, right? So this is a sequence-based execution language. So it will start from the left to right. And first we see 2. We just copy the 2 to the stack. And we see 3. We move to the next instruction. We see the value. Then we will also copy that. And then we see add. So we'll copy that to stack. And since this is an operation, it will be interpreted by the interpreter. And so remember, add is nothing but it take 2 preceding numbers and do addition. So the result of that is it will take 2 and 3 out, and then it will replace with 5, because the result of 2 plus 3 is 5. And then we come to this point. Now we executed add. We have again 5. So we just simply copy 5 on top of it. And then we come to the last step, op equal. So we copy this op equal onto the stack. And then we execute the op equal. So it checks the equality between the 2 preceding numbers, 5 and 5. Since it is equal, then it will replace the stack and it will give you true. Any questions or comments? If you don't know how stack-based languages works and how compilers works, actually, it's a bit difficult, but this is how the step-by-step execution happens, right? So follow the simple rules. whenever you see a value, you copy on top of the stack. So you will go to the stack and top of the stack. And the second rule is whenever you see an operation, you will compute this operation, you will execute this operation, and you will replace all the values which are part of the operation. For example, maybe run more, let me run one more time. So whenever you see an operation, when we execute them, we replace the operation and also the values participated in the operation. So the add operation will take these two values, right? Entire things with the result of this execution. So now we get 5, and again we see a value of 5. So and things like that. Are we good? Or any questions? Okay, so is there a question? Yeah, understood, sir. Okay, good. Okay, so then, yeah, now let me get back you into this mood of locking and unlocking script, right? So let's say that we have this stupid script where we are trying to verify whether 2 plus 3 is 5. If we imply this to the Bitcoin way of thinking about locking and unlocking script, how it would look like. So this is how locking script look like. So the locking script will look like this: 3 op get 5 and op equal. So basically I'm taking this part as a locking script, right? This is the condition which we are specifying. And what is the unlocking script for this arithmetic addition? So 2 is the unlocking script. The reason is when you put 2, the unlocking script and locking script, it should validate correct, right? So for example, let me ask a question saying that, what happens if I use 4 as unlocking script here? Does it give any error? Does it give anything? So what I mean to say is I have the locking script like this: 3 op add 5 and op equal. And then I'm trying to say that rather than using 2, what happens if I use 4 as the unlocking script? Anyone? Where exactly it will fail? Okay, so what I mean to say is let's put 4 as the unlocking script. So then this whole script will become 4, 3, op add 5, op equal. So 4 plus 3, we will do all this addition and you will get 7. So in this place, you have 7 and you will copy 5. And then the op equal will verify whether 5 is equal to 7 or not. And then, which is not, you will get a fail. You will get a fail or you will get a false. Right? So the result of having 4 as unlocking script will give you false as the output. Right? Okay, so let's go further. Now I want to execute this horrible the script which you have seen before, right? So to redeem a previous transaction, to check if a transaction is correctly redeems the output, we create a combined script by using the script public key, which is referred as the locking script. And we combine with the script signature, which is unlocking script, right? Which we put the script signature on the top, and we put the script public key, the locking script in the bottom, and the unlocking script on the top. Right. So the whole the instruction looks like this. So you have op check signature, op equal verify, public key hash, and op hash 160, op duplicate, and then we have the public key and we have the signature. Right. So this is how the scripts are constructed. So this is this part of the script is generated when Alice transferred coins to Bob. So this is the script public key, or you can say this is the locking script. And signature and public key, this is the unlocking script, which is generated or which is used when Bob is spending his coins, right? And one more thing to remember is public key hash is contain a hash, which indicate that we just want to verify whether the hash values equal or not, right? So that is the one. Okay, now let us execute this step by step, right? We have all the instructions like here. What we did is we took a unlocking script and we put on top of the locking script. So this is the unlocking script and this is the locking script. We put on top of each other, and we simply, since this is a scripting script, we simply execute step by step, right? So basically, let's do it here. Now we see signature. We just copy the signature here, right? So signature Bob, I put underscore Bob just to indicate that to match this example, right? So we put the signature of the Bob onto the stack, and then we come to this execution level. We copy the public key. So we completed this step. We completed this step. Now public key is on the stack, right? Again, I put public key underscore B just to indicate that it is Bob's public key and things like that, right? Now the locking script is added onto the stack. Unlocking script is added onto the stack. Now let's go to the locking script part. So you have op loop. What does it mean? It is nothing but in its operation saying that duplicate the values. So that means copy the values onto the stack, right? So this operation will take the topmost value and it will duplicate and copy to the stack. So that is what it does. So you can see here, it takes public key underscore B and it create a new copy and copy it to the stack. So now we have the public key, the two, how can I say, two instances of the public key in the stack, right? And now we completed op loop. Now let's go to op hash 160. So what is hash 160? Remember, we have discussed this hash 160 when we are discussing about the keys. So basically what we do is we take a public key and hash it 2 times to get and use a hash 160 function to get a hash value, right? So this is nothing but given a public key, it computes the hash value of it, right? So it will say hop hash 160. So that means let me roll back one step backwards. So So sign public and copy the public key and duplicate the public key. We did it, and now we get this hop hash 160. So basically, what it will do is it will take the top value in the stack, and it will compute the hash 160 value here, and it will replace it. Remember, whenever you have an operation, and when operation performs some steps on the stack, the values included in the operation will be replaced, right? So when I execute this value, what will happen is, since this is the value on which the operation is operating, so it will replace this value with the hash value. So that is what happened, public key hash. Now it computed the hash value of the public key, and it replaces the public key, right? So now let's go to the next step. So we have the public key hash. Again, remember the syntax here is all the values are indicated using these angular braces. So if you see an angular brace, this is nothing but a value, right? So now we see public key hash. Where do we get it from? So from this one. So we simply copy that to the stack. So now you see the public key hash. And the next thing is op equal verify, right? So op equal verify is nothing but an operation which checks whether the two values in the stack are equal or not. And remember, always stacks goes from the top to bottom. So it will take the two preceding values, the top two stack values, and then it will check whether they are equal or not, right? And remember, the result of this operation will replace the existing values. So basically, it will take away these two values and put the result. Yeah, right? So that means which gives a true. And now we'll get back to the check signature. And yeah, when the check signature basically takes the signature, this is the public key, and this is the signature. It will just verify whether the signature is generated with the private key connected to this public key, corresponding to this public key, right? If that is valid, it returns true. Let's say that the coins are transferred to Bob, and let's say that if Carol has put his signature, and then at this step it will fail and it will return false. So that means if you are trying to spend somebody's coins, then you will get a false, and the script will throw false. The script will fail. Script validation will fail. Okay. Any questions or comments? Do you want me to run this animation one more time? Or you got it? Let's see. Yeah, okay, I will do it one more time, right? So, okay, so what we are trying to do here is basically we are combining the unlocking script with the locking script. What does it mean? Bob is now spending his coins. So this is the unlocking script. Bob is putting his signature and things like that. So this is the signature, this is the public key, this is the information which he will use to spend his coins. And we combine that with the coins where Bob got from, right? So Bob got coins from Alice. So that is the locking script. We combine unlocking script and locking script and just combine it together and we execute them, right? So this is a stack-based language. So basically here you have these two things put together. So which is nothing but a sequence of serial instructions, right? So we execute them one by one, right? So that's what we do. So the first step is the signature. Since this is a value, because it is wrapped with this angular braces, so which indicates a value. So remember, whenever we see value in the stack-based language, we just copy it to the stack. And where do we copy to the stack? Always copy to the top, right? So since we don't have anything on the stack is empty. Now we copy this value. So we have the value here, right? It is the same value. I just put underscore B just to apply to this Bob's example, right? So, but otherwise it's the same value. And we go to the next step. We have the public key. Again, it's a value. What we do is we just simply copy onto the stack. So we have the public key now, right? We go to the next step. And now we have an operation. It's op dup. What does it mean? It will duplicate the value, the top value in the stack, and copy a new value, right? So it will basically take the copy of the existing value and create a new entry in the stack. Basically, we just want to duplicate the values. Why do you want to duplicate the value here? Okay, let me run the animation, and then meanwhile you can think why we need this duplicate operation and what happens if you take away the duplicate operation, right? So we take this duplicate value operation, so it will create another copy of the key, copy to the stack, and we go to the next one, and which is nothing but computing the hash value of the public key. So let's execute that one, and public key hash is computed. And remember, this is whenever an operation is executed, all the values included in this operation will be replaced. So we replace the public key with the public key hash. That's fine. And go to the next step. We have the public key hash. Again, this is a value. We just simply copy the stack. The value is copied to the stack. And then we see op equal verified. Now this is an operation. What it will do, it will verify whether two values are equal or not. So basically, it will take the top two values in the stack and see whether it verifies. Remember, all the values in the operations involved in the operation will be replaced. So since this is a binary operator, so it will replace these two values and put the result. So let us say that if we get true, and yeah, I didn't put true in the animation, but whenever it fails, then it throws the fail and things like that, right? So imagine that it has validated correctly. So that's fine. And then we have the object signature, right? So again, this is an operation. It takes two values. It takes the public key and it takes the signature, and it will verify whether the signature is generated with the corresponding with the private key of the connected corresponding public key, right? So basically, what it will do is it will generate whether signature is generated by Bob or not, right? And this is the public key of Bob. So it will verify whether the signature is generated with the private key of the Bob. Remember, how do we generate a signature? Bob will use his private key to generate to sign a hash value, and that is the signature. Since Bob has used his private key, we can use his public key to decrypt and see whether the contents will tally. If it tallies, then the signature is valid, right? So let us say that we executed op signature and everything looks good. So we get a true one here. Okay, so my question is, do we need this op duplicate here? If you don't have op duplicate, what happens is, because you are trying to compute the hash, so you will end up overwriting this private key, right? So this private key will be gone and the signature will fail. So that is the main issue here. So that's why we need this op duplicate value. Okay, so let's go further. Now the script execution is executed correctly. So that means the transaction can be executed, right? Again, let me run this example using this the another book, right? So Mastering Bitcoin book. So again, we use a bit different syntax, but nothing to worry much, right? So again, we have the same things: signature, public key, dupe is an operator, hash 160 is again an operator, public key hash, and equal verify is an operator, check signature is an operator. The syntax is a bit different. The Arvind Narayan's book use op underscore, but here the operations are without any op underscore, but the script is the same, exactly the same, right? So we execute step by step. We copy signature here, and we copy public key here in the next step, and we verify duplicate, we perform duplication. So now you can see the public key is copied one more time. And then we get to the hash 160, public key hash is generated. And when we get to the public key hash, okay, so maybe to preserve the public key. Yes, that's right. So yeah. Is there any question? That's right. To preserve the public key, otherwise the public key is taken away and you have no way of validating the signature. So then we create the public key hash and we verify, copy the public key hash, and we verify, in the next step, we verify equal verify. And if it is equal, then those two values will be replaced. And if it is not equal, then it will throw exception immediately. Exception means it will simply return false immediately, right? So whenever an operation fails, it will return immediately false. It doesn't execute any further instructions, right? So, and then finally we have the true. We have the check signature, basically it will check whether the signature is made with the connected private key or not, and then it will verify. Right. So this is how a unlocking script and logging script put together executed in the scripting language. Okay, so let's go further. So the scripting language, it contains 256 operations and 15 disabled and 75 reserved for future and things like that. And most of the operations are arithmetic, like the addition, multiplication, division, those kinds of things. And it has the branching if and else, if and then, not else, only if and then. And then it has the logic, and it has the crypto operations like the hashing, signature verification, and multi-signature is also part of it, and things like that. Okay, any comments or questions? How far are you tired? So we started. Do you need a break? Maybe I think we have 40 minutes, 50 minutes. So we'll take a break and the 10 minutes break and then continue. Right?
Okay, Professor.